I'm going to introduce the lab for magnetic braking with Faraday. The purposes of the lab are demonstrating the time variation of magnetic field with Faraday's laws and making the computational model of the tube and setting the aluminum foil tube with the falling magnet inside aluminum tube. And here is my observational and predictional time result, and you can see the little gap of 2 times, and I think the differences come from the error resistance and other errors. These are main physics principles in this lab. Savarz's law to measure the magnetic force of the bar magnet, and Lenz's law to calculate the magnetic force of induced current, and the Faraday's law to understand the interaction between magnetic field and the electric field making the electromotive force. And the procedure of the lab is finding the magnetic north pole of the bar magnet with magnetometer F with measure F and measure the initial condition and dropping the bar magnet inside the tube from the north pole, and then estimate the time 5 more times and calculate the average time. And the reason we use the aluminum tube is the tube is the propyl conductive material, which readily make induced current, and the tube structure is ideal structure to observe the changing magnetic flux. And I set the assumption that the falling speed is going to slower because the induced current might impose the upward force, which has opposite direction with gravitational force. And this lab, the system is aluminum tube and the bar magnet, and the surrounding is the environment with no various materials. Here is my measured initial condition of the tube and bar magnet. I used the magnetic dipole, which I used the previous lab 3. And here is my here is my time result, and the average time is 1.323 seconds, which 2 times more than times outside of tube with same height. I categorized the possible errors, the systemic error as a systemic error, environmental magnetic effect, and as a random error, the wrong measurement like length, mass, or time. And here is my computational model. I set the initial conditions of tube and magnet, and then I made the equations to estimate the magnetic field for bar magnet, induced current, magnetic force, and net force. And then this is my tube model and the graph of the bar magnet velocity by time, and you can see the flat part here, which means force equilibrium with the gravity and magnetic force. For the what if questions, if resistivity of the tube is closer to 0, then current will increase infinitely, and the magnetic force of bar magnet force will increase to as making the bar magnet fall slower. And if holes or slots were cut into the tube, then the current will decrease, the magnetic force will be and the magnetic force will be weaker. Then the magnet falls faster than we expected in our lab. And this is my interpreting questions. The red ring is the clockwise, the blue ring is the counterclockwise current. And if the flip the tube, then magnetic will fall faster, and the real world total time will take longer than because the air drag force. And as I said, at the flat degree of the graph, the gravitational force and the magnetic force by the induced current are same by opposite direction, and zero force without acceleration. Thank you.